Hello friends, in the last lecture we were discussing about the four noded quadrilateral element and we have completed all the relevant derivations, relevant stiffness matrix, load vectors and all that, and I have already solved one problem and one more problem I was about to start. So today let us complete that problem and then we will go for the next topic. See, in the last class, what I had given, there was a quadrilateral which has been given. This is the quadrilateral. Here, the coordinates are given 2, 1, 5 and 2, 3, 7 and 6, 4, 1 and 5, and there is a point P whose coordinates are given, x and y are already given to you. So we need to find out the values of the zeta, eta at that given point in the natural coordinate system, and then we have to verify whether that whatever we have found out is going to match with these two coordinates or not. So let us quickly note down the existing coordinates x1, x2, x3 and x4. See, if you look at this, this is 2, this is 5, this is 7 and this is 1. If I want y1, y2, y3 and y4, once again if you look at this, y1 is 1, 2, 6 and 5. Okay. In all that, we know the coordinates 6 and y is given 4. These are already known to you, so we need to find out that. Okay, so here what we know, we simply know that I can express the x in terms of all these coordinates by using the shape functions. So first relation what I know is x is equal to n1 x1 n2 x2 plus n3 x3 plus n4 x4. What is this n1? As you are already knowing, 1 by 4. Let us take like this. This is what is this? 1 minus zeta 1 plus zeta x1 plus 1 plus zeta 1 1 plus eta. This is, of course, this is a 1, this one, this is plus and this is minus. Okay, so this is your x2, this is 1 plus zeta 1 plus eta, which is x3, and lastly it is 1 minus zeta 1 plus eta x4. This is what we are already knowing how to find out this relations you are already knowing. Since I don't know the zeta and beta value, what I will do is I will take 1 by 4 as it is inside. This product, what is this product will give you? It is a 1 minus zeta square. It is nothing but, I can rewrite this. Okay. See, this is going to be, if I expand this, what will happen, you tell me? If I just expand, this is of course 1 minus eta, 1 minus eta. Okay, if I expand this, what I will get? This I will get. The value of this will be 2. Okay. This is value is 2. x2 is 5. x3 is 7. And x4 is 1. So what I will do is I will expand these brackets and multiply by 2 in bracket. So what will happen? This whole thing is 2 minus 2 zeta minus 2 eta plus 2 zeta eta. This is going to be the first expression. Then when it comes to the second one, that is 5 plus 5 zeta minus 5 eta minus 5 zeta eta. This is for the expansion of the second bracket. Now let us go to the third one. 7 plus 7 zeta plus 7 eta plus 1. This is for the next one. Then coming to the last one, it is 1 minus zeta plus eta minus eta eta. This is all good. Of course, 1/4 is there. So you just take the terms 2 zeta, 5 zeta, 7 zeta, and 1 minus zeta here. Similarly, you group all these things like constants 2, 5, 7, and 1. This is going to be the constants. Then eta terms like this 2 eta, 5 eta, 7 eta, and 1 eta. This is all. So if you club them, what finally you are going to get this is 1 by 4, 15 plus 9 zeta plus eta plus 3 zeta eta. But you are already knowing that the value of x is given here, that is 6. If I take 6 here, 6 equal to this. So therefore, if I multiply this, what I will get is 15 plus 9 zeta plus eta plus 3 zeta eta is equal to 24, because 4 3s are. So this is the first equation, what I am going to get this here. In the similar way sense, if I write, this is going to be n1 y1, n2 y2 plus n3 y3 plus n4 y4. In the same manner you write it, that is 1 by 4, 1 minus zeta, 1 minus eta, y1. y1 is 1 here, I will substitute that 1 here, plus 1 minus zeta, 1 plus eta, okay, this is 1 minus eta, right, okay, that is equal to y2, that is 2. Whereas next, this is 1 plus zeta, 1 plus eta, y3 is being 6, plus 1 minus zeta, 1 plus eta, y4 is 5. So if you substitute like this, so what you will get is this one. So now again expand them. What is this now? Because here if I expand it, 1 minus zeta minus eta plus zeta eta plus 2 plus 2 zeta minus 2 eta minus 2 zeta eta plus 6 zeta 6 eta plus 6 zeta eta. Firstly, plus 5 minus 5 zeta plus 5 eta minus 5 zeta eta. So, in the similar sense, like this, what you got, you can again get it. This will come 1 by, see y. What is y? Y is now 4. So, therefore, 4 equal to 1 by 4 into bracket. So, when you do all these things, 14 plus 2 zeta plus 8 eta plus 0 zeta eta, because there is no this thing is going to come there. So naturally, if I take this here, it will come 14 plus 2 zeta plus 8 eta is equal to 16. This is what you will get as the second. So you can reduce it. So what is this first one is going to come? If you take 15 this side, what will happen? This equation, I will write it here, 9 zeta plus eta plus 3 zeta eta is equal to 24 minus 15. 24 minus 15 is nothing but 9. So this is coming as another, let us say, 3. Similarly, if I take this here, 2 zeta plus 8 eta There is no this one. This is equal to 16 minus 14. This is equal to 2. This is the fourth equation. Now I have to solve this. How do you solve this? You can simplify this still. This can be written as zeta. Okay, I'll modify this. 2 I can take it out here. Zeta plus 4 eta is equal to 1. Or zeta is equal to 1 minus 4 eta. So this is going to be the final answer what you are going to get this. So wherever this zeta is there you can put that. That means I can take any one of them, you can write that. For example, I will take the first one. What will happen? Okay, now let us substitute that value of zeta and I will replace zeta by eta only. So all these terms will be coming there. Let's see how exactly we can put that. Okay, first equation what it says 9. 9 1 minus 4 zeta. This I have taken. Plus eta is remaining like this only. Plus 3. 3 what? Zeta eta. So 1 minus 4 eta into eta. Okay, this is equal to 9. So what we will get? So what is this? 9 minus 36, this is eta only. 36 eta plus 3 zeta minus 12 eta square is equal to 9. This is what you are going to get this. If I take this on this side, what will happen? 12 zeta square. Because this I will go, this 9 will become 0. Then what is this zeta? 36, this, okay. 36 minus 4, that is 32. That is minus 32 eta, because this 3 plus eta is 4 zeta. 36 minus plus 4 zeta is minus 32 zeta. This is equal to 9 minus 9, which is 0. So, but it is a quadratic equation. See, of the order what? If I want x1, this is like you know it, ax1 plus bx plus c equal to 0, where x and 1 roots, if you want, minus b plus or minus b square minus 4ac upon 2a. Correct? So, in the present equation, when you look here, what are the things you tell me? 8xa is going to be 12, b is going to be minus 32, c is going to be 0, because there is no term with constants, so it is going to be 0. So, let us substitute that. So, therefore, if I want the quadratic equation, zeta 1 and 2, if I want, minus b is 32, plus, okay, 1 second. Yes, I can take out something from this. Still I can write this instead of 32, 4. I can make this as 4 is 3 za. Okay. This will be 4 3 za, and this is 8 eta equal to 0. That also one another same. I have taken 4 outside, then that will be that. So this will be 3, this will be minus 8, this will be anyway 0. So therefore, this will become 8 minus 8 will become this square root of b square minus 4 ac, this is 0, upon 2 into a is 3. So what will happen? This is 8 plus 8 upon 6. This is, of course, this will be 0. So, what are the two options? You will be having that. So, if you look at the first function, if I take minus sign, this will be 0. If I take the second, it is 16 upon 6. Correct. Minus 12 square, this is that. So this will become plus, correct? Yeah. So this will become minus minus plus, and this is minus square. So therefore this will be there. And this is minus 16 by 6, which is minus 2.67. There are two roots here and here. In the similar manner, you are knowing that zeta is equal to 1 minus 4 eta. So this is, if you take the first root, 1 minus 4 into 0 is 1 only. If you take the second one, that is 1 minus 4 into minus 2.67, if you take like this will be how much? 11.68. Now it means again I have two roots for this and this. Out of this, which one to take? See, for any element when you are talking about fourth quadrant, the most important point what you have to remember is, if you call this as zeta and this is eta, they vary from minus 1 to plus 1 only, and this is again minus 1 to plus 1 in this manner also. So the maximum value, zeta and eta always lie between plus 1 to minus 1. It cannot be more than that. So obviously when I take this, there is no possibility of this. So only possibility is zeta 1 equal to 0, and the next possibility is this one, that is 1. It cannot be this. These two are not possible, because the maximum range in which zeta and eta varies are minus 1 to plus 1. So here also minus 1 to plus 1, plus minus 1 to plus 1. So therefore our final values, what you can say, final values are zeta equal to 1, eta equal to 0. So these are going to be the natural coordinates, you can say, of the given point 6 and 4. But how to know that this is correct or not? We'll just quickly check that. These things we'll just quickly check, because we know that the final answer for x and y is already known to us. They have been given, that is 6 and 4. Whether these values what we have found out, 1 and 0, are they matching it or not? How to check that? Tell me. You use like x, for example, x you find out. X equal to what? 1 by 4, 1 minus zeta, 1 minus eta, x1 that is 2, plus 1 minus zeta, 1 plus eta. Okay, this is 1 plus and this is 1 minus. Y2, x2 is 5 plus 1 plus zeta, 1 plus eta, 7 plus 1 minus zeta, 1 plus eta, 1. Okay. So this answer, it should come 6. Then only our answers are correct. So let us try this. 1 by 4, I will take zeta equal to 1. So that means this is going 0. This is 1 minus 1, 1 minus 0. No problem. This is 2. So this is gone. Next one, if I put here, it will become 2, 1 minus 0 into 5. Okay, fine. This is that. Next also it becomes 1 plus 1, 2, 1 plus 0 into 7, plus 1 minus 1, 1 plus 0, 1. So this is also 0. So that is also gone. So finally what is remaining here is 1 by 4 into bracket 5 into 2, 10 plus 14. So this is going to be 24. 1 by 4 into 24. So this answer comes 6. And we are already knowing that the value of the x given here is 6. That means these two natural coordinates are perfectly matching. That is 1 and 0. We can just check. Even y also should come same. That is 1 by 4. First one anyway it is 0. That is, there is no need of this. Second one, it is 2, 1. What is the y2? That is 2. y3, it is 2, 1, and y3 is 6. Then the last one is again 0. There is no need of finding that. So here it will be what? 4 into bracket, 2 into 2, 4, plus 2 into 12. So this is 16 by 4. So which is coming 4. See, we are already knowing the second coordinate. So that means the given, you can say zeta, eta, what you have found out are in perfect agreement with the whatever you can say coordinates which are given here, x and y, they were given here and they are perfectly matching with those values. Okay. Now, see, let us quickly go to the next topic. First, one important point you remember, when we were discussing about constant strain triangular element with the 3 sides, all the 3 sides are straight sides. That is, there are 3 straight lines which are connecting the triangle. When we are going for 4-noded quadrilateral triangle also, all the 4 sides are going to be straight only. What I would like to say here is, if you have an approximate curved boundary, and if you discretize this curved boundary, irregular shaped boundary or a curved shaped boundary, with these type of elements, because of this straightness, however smaller element you use it, maybe the number of elements will definitely go very high, because you have to close those curved portions by straight portions. But still, the FEM model and the original configuration of the object, they will never match. There will be a small amount of error because you are approximating the actual contour, which is the straight-sided contour, and there will be definitely loss of data and loss of you can say area is considered. Therefore, the results are not that accurate. Then is there any chance that we can go for special elements which will take care of even curved boundaries also? And if you look at the, you can say, shape functions which are associated with, you can say, 3-noded to a simple zeta, eta, and 1 minus zeta, eta. That is, you have only 3 choices, 1, zeta, and eta. Even when you come to your 4-noded quadrilateral also, there also we find out only 1 and zeta and eta only. There are no any higher order terms in like terms like zeta square eta or zeta eta square or zeta square eta square. See, the moment the order of the polynomial goes on increasing, the accuracy of the results will also increase. So therefore, if we can develop certain elements wherein the shape function contain higher orders like zeta square, eta square, like that, if you have such type of quadratic values of zeta and eta, then our results are becoming more accurate and you can map even curved boundaries, because the square terms are nothing but they are higher order terms. So our approximation is going to be more accurate. So such type of elements which are taking care of even curved boundaries and all that, they are called higher order elements. Today what we are discussing is now higher order elements. Okay, there are 3 types of elements. One is 9-noded quadrilateral element. Then we can take 8-noded quadrilateral element, and the other one is 6-noded triangular element. Okay. See, all the other relations for all the 3 elements are remaining the same. That is, if you want U, since it is a 2-dimensional element, it always consists of U and V only. And this is going to be N Q, where the number of degrees of freedom and for the elemental level depends upon the number of nodes. For example, if you have 9-noded quadrilateral element, in case if you take 2 degree of freedom per node, it will be 18 will be the size of this cube, 18 by 1. If you take 8-noded quadrilateral element, 8 nodes are there, total number of degrees of freedom are 16, so that will be 16 by 1. Similarly, if you take 6-noded triangular element, it is 12 by 1. That will automatically change, and the size of the shape function will also change that. So next, if you come across the strain strain is again one and the same, but these B and Q, when you look at their sizes are depending upon this. Of course, you remember that these are going to be 3 by 1 only. This is again going to be epsilon x only, epsilon y only, and gamma y only. For all 2D elements, the stresses, these three components of stresses are always going to be given. So that is going to be given by this equation. And similarly, lastly, the element stiffness matrix, what we have developed, will be following the same relation, that is -1 to +1, -1 to +1, B transpose C into B into determinant of J d zeta d eta. This is going to be common for that, but only the size of this depends on that. That is what I told you. First one is going to be 18 by 18, 16 by 16, 12 by 12. That is the size of the element stiffness matrix, and we need to go for it. So with that, let me quickly go for the first type of element, which is called a 9-node quadrilateral element. First, let me draw the general drawing of the element, the Cartesian coordinates. Then I will draw the master element, and then we will draw the remaining part. Look at the node numbering 1, 2, 3 and 4. These are always corner nodes, and the mid nodes are 5, 6, 7, 8, and the 9th is the, I can say, center node. This is what we call it. So therefore, if we consider this, of course, this when you say zeta is equal to -1, this is going to be zeta equal to +1. This is zeta equal to +1, and this is zeta equal to -1. So this we'll try to represent it on a master element. We call it. It is always going to be square. This is a square element with all the 9 nodes. Zeta and eta. So 1, 2, 3, 4, 5, 6, 7, 8, 9. See, always this is the origin, which is going to be there. This is always -1, 1, -1, -1. This is always +1, +1. This is always there. Here, this is going to be 1, -1. Here, -1, 1. This one. And when it comes to here, this is what? This is going to be along this. Eta is 0 here. So therefore, this is 0, -1 it is. Because eta is -1. This is there. And this is going to be 0 + 1. This one. And what about this? This is on this one. So therefore, 0, no, not 0. It is -1, 0 here. Here it is 1, 0 here now. So these are the, you can say, coordinates of these 9 points. So let us consider first the zeta coordinate as one element. I will take this as zeta. I will name them as 1, 2, 3. In sequence, naturally this is going to be -1, this is 0, and this is +1. And similarly, you want a eta coordinate, it is going to be like this. You take like this, like this. You consider this as 1, 2, 3, and these are obviously eta equal to -1, eta equal to 0, eta equal to +1. See, I am trying to develop the shape functions for these 9s, because obviously I have told you the number of shape functions n1, ni, what do you call? I depends upon the total number of nodes. For example, in this case, since there are 9 nodes, there are going to be 9 shape functions, that is n1, n2, n3 up to n9. But when you look at this, there are 2 coordinates. Since both zeta and eta are there, so both have to be considered here. So therefore, first let us consider zeta, and then we will develop this. Okay. Let us call it as, let us define 3 generic, let the generic shape functions, we call them as generic shape functions, as L1, L2 and L3. These are there for both of them, but in the bracket if we refer L1 of zeta, L1 of eta like that, they will be more specific. Now, what are the property of this? See, this is again as usual Li is equal to 1 at node I and it is 0 at other nodes. Okay. So let us consider this now. So Li, okay, Li or L1 of zeta is 1. It is 1 at zeta equal to -1, and it is 0 at 2 other things, that is zeta equal to 0 and zeta equal to +1. So it has to be 0 at these 3 values. So therefore, if I want to find out this, first if you want to satisfy this, L1 of zeta must be equal to, if you put zeta, it has to be 0. If I put +1, it has to be 0. So therefore, it has to be of this form. Then only you can put 0, this L1 will become 0. If you put +1, this will become 0. Constant C is to satisfy the next important equation. What is that? 1 equal to C, zeta is going to be -1, that is -1 and 1 minus of -1. So which is going to be -2C. So therefore, C is equal to -1/2. This is what you will get. So therefore, if I want to write down my L1 of zeta, it is minus zeta into 1 minus zeta upon 2. You can see this is going to match that. The similar way, if you want L1 of L2 of zeta, if you want, it is 1 at zeta equal to 0, please remember, and it is equal to 0 at zeta equal to -1 as well as +1, because it is at node 1 and 3, the value of L2 is going to be 0, but at node center 2, it is going to be 1. So how to satisfy this? To satisfy this, L2 of zeta has to be of the form 1 minus zeta, 1 plus zeta. So that whatever you put here, that will become 0. But when I put this, what will happen? 1 equal to C. If I put zeta equal to 0, zeta equal to 0, it simply says C is equal to 1. So meaning of this is L2 of zeta is 1 minus zeta, 1 plus zeta only. So C, since it is 1. In the similar sense, I can write L3 of this thing is equal to zeta 1 plus zeta upon 2. See, on the basis of these three, you can say generic functions are generated. In the similarly I can find out now same thing, that is similarly L1 of eta, just you replace that is minus eta, 1 minus eta upon 2. Okay. Then L2 of eta is equal to eta into 1 plus eta, sorry, this one will be 1 minus eta, 1 plus eta, and L3 of eta is equal to minus, not minus, eta into 1 plus eta upon 2. These are going to be what are called as this one. Now the question comes is how to find out these are not the shape functions. Shape or function at a given point, when I want to find out, look at this. This is the way I will write now. See, if I take this, see here, how many nodes are there? Totally 9 nodes. So these are the 8 and the center one. Okay. So if I write here, if I write here, if I write here, and if I write here, write here, write here, what are these? 1, 5, 2, 6, 3, 7, 4 and 8. And this is 9. Now, see here, this you are already knowing that this is zeta coordinate, it is eta coordinate. So therefore, this one, when you want to start, node 1, this is L1 of eta, L2 of eta, L3 of eta, this one. When you come to this, this is all zeta, this is L1 of zeta, L2 of zeta, L3 of zeta, this one. So naturally we have totally 9 shape functions. If I take this, for example, if I call it as N1, it is the product of these two, L1 zeta into L1 of eta. Okay. So now let us write that, L1 of zeta into L1 of eta, the two products. Next comes N5. Okay, let me take N5. What is this? It is the product of what? L5. It is again L2 of zeta now here. But as far as, since it is on the same line, L1 of eta only will come. And similarly, if I want the last, that is N2. N2 is what, tell me? It is going to be L3 of eta into L1 of eta only. This is that. Next horizontal line you come, it is N8, N9, N9 and N6. Okay. And the last row says N4, N7 and N3. Okay. And now see here, what is this N8? N8 is going to be L1 of zeta and L2 of eta. L1 of zeta, L2 of eta. See here also L1 of zeta, L3 of eta you will get. These are all L1, these are L1, L2, L3. Here it is again L2, L2 only, zeta, zeta. This is L2 of eta, L3 of eta. You can just check. N9, what is this? L2 and L2. That is what exactly is reflecting. Here all three will remain same. First, that is L3 of zeta will remain. Here also L3 of zeta will remain same. This will become L1, L2 and L3 of eta. So this is what exactly what I want to say here. See, for example, if I take this N1, N1 should come if I put, for example, you know, N1 is always 1 at zeta and eta equal to -1, correct? Just to cross check for you, I will show this. Okay, let me cross check and show you. See here, N1 is 1 at zeta equal to -1 and eta equal to -1. And this is the product of L of zeta, L1 of eta. This is the product that we have already defined. What is this? L1 is equal to minus zeta 1 minus zeta upon 2 minus, okay, this is in bracket, minus eta 1 minus eta upon 2. Let us put these values. What will happen? Minus of -1, 1 minus -1, this is there, upon 2, right? This will be minus of -1, 1 minus of minus 1 upon 2. So this will be nothing but 2 by 2, because 1 plus 2, 2 into plus 1, that is that, into 2 by 2, which is equal to 1. Therefore, we are knowing that this condition will satisfy for the given values of anything, any product you take. Simply, for example, if you take here, you can just take, for example, 0, 0 here, N9. When you say N9, if you take this, if you put the values of 0, 0 in this N9, it will come 1 only. And N9 will come 1 at the coordinates value of zeta and eta equal to 0 and 0. Okay. So this is what I wanted to propose. Here, only the shape functions are sufficient. Other things are routinely we can find out. Maybe the amount of calculation is going to be little large, but the procedure for finding the U matrix, strain matrix and stiffness matrix and all other things will remain same. Only we need to define the new shape functions for all these new elements, higher order elements we call it. So in the similar manner, let us quickly go to the next element, which is called as quadrilateral. This is 8-noded quadrilateral, which is also called as, it is belonging to the serendipity family we call it. 8-node quadrilateral element. Here the element comes like this. Here there is no midpoint node here. Here there is no node, only 1, 2, 3, 4, 5, 6, 7, 8 only. Okay, here there are no nodes here. And this is of course in the x and y coordinate. This is minus 1. This is zeta equal to plus 1. Zeta equal to plus 1. Zeta equal to minus 1. And if you develop the master element, this is called as the master element. Master element is typical here. We can take like this. You know the coordinates. This line is zeta equal to minus 1. This is plus 1, this line. This is zeta equal to plus 1. This is equal to zeta equal to minus 1. What is important here is this plus this is equal to 1. Therefore, I write this line as zeta plus eta equal to 0 about this line. Whereas when we want this 1 minus zeta plus eta equal to 0, this is here for this line. 1 minus zeta minus eta is equal to 0. 1 plus zeta minus eta is equal to 0. See, this is the meaning of this. See, what I want to say here is, here all the 8 nodes cannot be taken. For example, if I take only 1 and this is 5 if you take and this is 2, this need to be 0 at all these points. You can see here, this is going to be there here and this is going to be there here and this is going to be here now like this. This is going to be in that manner, we can join that. Therefore, this is going to be 1 at these 2 points. In the similar way, when you take 4 corners, all the relations are same. But when it comes to the 5th node, for example, if I take 5th node, N5, if you take it as 1, this N5 equal to 1, when you join this to this and maybe this and this and this, all this when you take, what really we find it is this is the triangle which is in this plane, vertical plane, and remaining all these are 0. That means this is 0, this is 0, this is 0. That means this is equal to zeta equal to plus 1, this is equal to zeta equal to minus 1, and this is zeta equal to minus 1, and this is plus 1, right, like this. So along these three edges, okay, the value of n5 is going to be 0 for along these three edges, and n5 is 1 at node 1. So due to this different type of property, at a time I cannot solve all the 4 shape functions here. So therefore, first I will define first 4 functions, n1, n2, n3, n4, and then I will define the remaining, that is n5, n6, n7, n8. So let us quickly look at that. This is also called as element belongs to serendipity family. Okay, this is called serendipity family. Okay, right. This is the special element which belongs to serendipity family. Now let us write, first develop only n1 to n4, then we'll let us say afterwards we'll develop the shape function for n5 to n8. Okay, now what are the properties of n1? Let us see. Ni. Okay, Ni we want to find out. So what it should be? n1, if I want n1, it should be in the form of, see, n1 if I take, it should be 0 along this edge, should be 0 along this edge, and it should be 0 along this edge. So therefore, if I want to make this as 0, it has to be of 1 minus zeta, 1 minus eta, and this refers to 1 plus zeta plus eta. Okay, so that means when we take yes, see what is the meaning of this? If you look at this, n1 is 1, okay, whereas along this edge and along this edge it is 0. That means this is zeta equal to plus 1, this is zeta equal to plus 1. So along these two edges, obviously n1 is always 0. Remember, because in other way it is not 0. In other way here there is a continuous variation here, that is not possible. But when you come to this, along this there is no variation of n1 along this. So to meet this, it should, whenever I substitute zeta equal to plus 1 and plus 1, it should become 0. So that will take care of these two. And along this line also it should be 0, that is referred to that. So that is the reason I have taken this is C. Now I have to find out the value of C. That is n1 is 1 at zeta equal to minus 1 and eta equal to minus 1. Correct? So naturally what is this? 1 equal to C, 1 minus of minus 1, 1 minus minus 1 into bracket 1 minus 1 minus 1. If I write this will become 0, this will become 2, 2, okay, 4. So C will become minus 1 by 4, it becomes 1 by 4. So accordingly, my shape function n1 is becoming 1 minus zeta, 1 minus eta, 1 plus zeta, eta, and C being 1 by 4. So therefore, of course, this all with negative sign, because C is minus 1 by 4. So n1 of zeta, if I want, I will get this. I call it not zeta, it is n1 only, because n1 is containing both zeta and eta terms. So n1. In the similar logic, n2 will be defined 1 plus zeta, 1 minus eta, 1 minus zeta plus eta upon 4. n3 minus 1 plus zeta, 1 plus eta, 1 minus zeta minus eta upon 4. And in the similar form, n4 is equal to minus 1 minus zeta, 1 plus eta, 1 plus eta minus eta upon 4. So this is going to be what is going to be this one. So therefore these are the 4 shape functions first we have to define. Now to define n5, n6, n7 and n8. Come on, what are the possibilities I told you? I have already told you the n5 is 0. Along what edges tell me? Zeta equal to minus 1 it is 0. Zeta equal to plus 1 it is 0. Zeta equal to plus 1 it is 0. So therefore at all these 3 it is going to be 0. So that means if I write it as zeta, zeta equal to minus 1 means 1 plus zeta, 1 minus eta and 1 plus or 1 minus eta. Correct or not? This is what I need to find out. Zeta is equal to 1 plus zeta. No, not this. This is 1 plus 1 minus zeta, which can be written as, and obviously the C need to be found out. What is that C? n5 is 1 at zeta equal to what? What is the value of zeta? It is 0 and eta equal to minus 1. Correct? So therefore if I substitute in that, what will come? 1 equal to C into bracket 1 plus 0, 1 minus 0, 1 minus of minus 1, which is equal to 2C equal to 1. So therefore C is equal to half. Correct? So therefore if I multiply this I can write it as 1 minus zeta square 1 minus eta upon 2. I can write this. Because a plus b into a minus b is a square minus b square. I can write it as 1 minus zeta square these 2 into 1 minus zeta, and c has come half because of this. Similarly, I can write the next one 1 plus zeta 1 minus eta square upon 2, 1 minus zeta square 1 plus eta upon 2, 1 minus zeta 1 minus eta square upon 2. So if you just take this, you will take care of. It is called 8-noded quadrilateral element, and these are the 8 shape functions. We are separately defining each one of them, and then first 4 we are defining separately, and the remaining 4 we are separately defining, and then we are compiling all of them. That is how we got 2 different sets of shape functions, which are all containing quadratic terms. You can see there is a reason. If you can see there, they carry eta square or eta square term, so that is the reason is always going to be, you can say curved boundaries can be easily mapped with using this type of shape functions. And quickly let us come to the last, which is called as 6-noded triangle, or it is also called quadratic triangle. 6-node triangle or quadratic triangle. Just to draw, these are the drawings. Again, it has got mid nodes here, 1, 2, 3, 4, 5, 6. Okay, this is written in x and y coordinate. When you come to the mapping, master element, these are the master elements. See, these are containing these 3, containing this, and these are containing these. This is zeta equal to 1, zeta equal to half zeta equal to 0, eta equal to 1, eta equal to half, eta equal to 0. And this one, we define another term here, that is zeta, gamma, like this. This is another 1 half and 0. Quickly to write, n1 is zeta, 2 zeta minus 1, n2 eta, 2 eta minus 1, n3 gamma, 2 gamma minus 1. Whereas n4, n5, n6 are 4 zeta eta, 4 gamma eta, 4 eta gamma. Of course, your u will become same, nq only, and x is equal to ni xi summation, y is ni yi, n1 y1 1 2 y3 and all that. The same relations are going to be maintained even in this also. So these special 3 elements what I have discussed today are called higher order elements, and they are having lot of application in FEM for finding the, or for mapping curved boundaries and all that. Okay, with this we are now completing the higher order elements here today. In the next class, okay, in the tomorrow, I will be discussing about axis symmetric solids, that is solids of revolution you can call it, like cylinders, cones, spheres, such type of solids of revolutions, which will be, though they are looking 3D in nature, but we can convert them into equivalent 2-dimensional problems. So therefore, how to convert a 3D problem into 2D problem, that I think we will discuss in the tomorrow's class. Bye.